So the first reason we're producing more lactate is because we're using these big muscle fibers that don't have many mitochondria. The second reason that we're going to shift towards carbohydrate utilization is because of this increase in catecholamines. So you can induce this shift in carbohydrate utilization by increasing epinephrine levels. And the reason that this happens, and you can see that here, if you go from 30 minutes and you look at 25, 65, or 85% of VO2 max, and you look to see what the epinephrine levels are, you go from 60 to 200 to 600. So you're increasing your epinephrine levels 10 times. So that's going to have big effects on which fuel we're going to use to power our bodies. And specifically, epinephrine is going to drive carbohydrate utilization at this high level. And the way that it does that is by inducing the first kinase cascade that was ever characterized. So this is the first one that was ever characterized. And it was basically characterized by Greta Corey and her husband Carl. But it was really mostly Greta who was the powerhouse behind this combination. And what they were doing was they were looking to try and figure out how it was that epinephrine caused an increase in glycogen breakdown. And so what they discovered is that epinephrine can bind to its receptor, and they discovered this enzyme cascade that involves the activation of a G protein, which activates this enzyme adenylate cyclase and produces cyclic AMP. And cyclic AMP activates a protein kinase called the cyclic AMP dependent protein kinase. So this is PKA is what it's called. So PKA can then phosphorylate and activate the phosphorylase kinase. Phosphorylase kinase can phosphorylate and basically change the activity of phosphorylase. And what phosphorylase does is that's the enzyme that induces the breakdown of glycogen into glucose. All right, so now what you've got is you've got epinephrine binding to a receptor and activating this increase in glycogen breakdown. So now you've got the second stimulus for increasing carbohydrate utilization. The first one, big muscle fibers without mitochondria. The second one is now you've got epinephrine coming in and driving this huge breakdown in glycogen to produce glucose 6-phosphate. And when you have lots of glucose 6-phosphate, that's going to drive glycolysis. And when you drive glycolysis, that's going to increase pyruvate. And when you increase pyruvate, that's going to drive more pyruvate into the mitochondria. And that's going to overwhelm the fatty acid utilization. And it's going to cause that traffic jam backup of fatty acid use. So now you've got this huge push where you're breaking down glycogen, you're producing glucose 6-phosphate, you're getting to pyruvate. If you have mitochondria, that pyruvate is going into the mitochondria and all you're doing is using carbohydrate because you've got so much of it coming in. If that is a bigger fiber and it has fewer mitochondria, now you're producing more lactate. So you've got all of these different things that are happening that are driving your glycogen breakdown, your production of lactate, your glycogen breakdown driving carbohydrate oxidation within the mitochondria if you have mitochondria. And you've got these bigger muscle fibers because you've got the bigger motor units driving more glycolytic energy production, driving more lactate production. How important is this enzyme phosphorylase? Well, these are a specific group of patients that don't have the enzyme phosphorylase. And these guys have what's called McArdle's disease. And so what Jim Hagberg did in this study was trying to figure out whether, does lactate cause you to stop exercising? And what he found is this beautiful thing. The dotted line is a group of normal subjects who have phosphorylase and are completely normal. The individuals here in black dots, those are McArdle's disease patients. They do the same increase in exercise workload where they increase their effort on a cycle ergometer. And what you can see is that blood lactate never rises. And so if you don't have this enzyme phosphorylase and you can't break down glycogen in response to epinephrine, you don't actually recruit. You don't actually increase lactate. But you still get muscle soreness and you still get you still get burning muscles and you still stop exercising. So what this shows us is that you don't need lactate at all to cause you to stop exercise, for your muscles to burn, all of those things. So that's not because of blood lactate. And the other thing it tells us is that it really, the shift towards glycolysis, the shift towards using carbohydrate as a fuel with increasing exercise intensity, is really dependent on epinephrine. Because epinephrine is breaking down and causing this activation of phosphorylase, breaking down glycogen, and that increase in glycogen breakdown is now going to drive lactate production. It's going to drive high intensity exercise. And the important thing to realize here is that these individuals, even though it says relative workload 100%, their workload is really, really suppressed because they can't exercise hard, because they can't use carbohydrate as a fuel. So even though they're going as hard as they can, they're not going nearly as high if you looked at the number of watts that their body was producing. The power that their body is producing is really depressed because they can't produce energy quickly enough to drive high amounts of power. Because they can't break down glycogen, they can't shift to using glycolysis, and they can't drive this huge increase in effort with bigger muscle fibers with more glycogen breakdown. Okay, so all of these things are telling us that the size of the muscle fiber is going to matter, because that also is correlated with the number of mitochondria. So if you want to increase how hard you can work at a high intensity, you need to increase the number of mitochondria you have within your biggest muscle fibers, the ones that you're going to recruit at a high intensity. And the other thing that's happening is that this increase in epinephrine is causing the activation of phosphorylase, the breakdown of glycogen, and now this huge influx of glucose 6-phosphate, which is powering glycolysis, it's powering glucose oxidation, pyruvate oxidation, or lactate production.